everybody, it's Mr. Clausen here. Just wanted to go over how to use Newton's law of gravitation in our class. So as we've already learned, we know that the law of gravity is a force of attraction between anything that has mass. And the way you calculate it is you take this number, this capital G, and you multiply it by m1, m2, and d squared. And we got that in lab. Now how that would work is, let's say, take a look, you or me, that's the little blue person there, was standing on the earth. How would we figure out the force of gravity acting on that person? And what I want you to notice is, we'll get to G in just a second, but m1, that would be the mass of the earth. m2, that would be your mass, my mass, or whatever object we are dealing with. And where we get the distance from is the distance between you and the center of mass of whatever object. In this case, it's the earth, or maybe whatever planet you're standing on. So the D just represents the distance between the center of mass. Now, technically, there is a difference between the radius of the earth and the distance between you, your center of mass, and the center of mass of the earth. But that distance is so small that typically when you do these problems, we just consider that the distance between you and the center of the earth to be the radius of the earth, just being the fact that the earth is so large. Now, some students have questions about what is the G value that we have there. Now, that's referred to as Newton's gravitational constant. And what it's there to do is it's just there to make the units work out. So we want our final answer to be force of gravity. We want that to be in newtons. But when we measure the mass, we're measuring that in kilograms, and we're measuring the distance in meters. And we have to put this number there just to make everything work out, to cancel, not to cancel out, but just to get the units to where we want them. But what I want you to notice here is something about Newton's law, or Newton's gravitational constant, and it's this times 10 to the negative 11th. Now what that means for scientific notation is that this number is actually 0.00, we got to get 10 zeros there, so that's 6, 7, 8, 9, and then 10. So it's actually this rate here, if you were to put that together. That's how big of a number Newton's gravitational constant is. And anytime you take a number and multiply it by like a really small number like this one is, what ends up happening is that number gets really small as well. So this is why the force of gravity is considered to be a very weak force, and we don't notice it until an object gets very large, like say the size of the earth. We don't notice gravity, say, between you and the table, because both your masses are relatively small, and when you multiply them then by the gravitational constant, while technically the force is still there, it's so small that you wouldn't be able to measure it or detect it at all. We need to have something very, very massive, like say the earth or the sun, before we get noticeable amounts for the force of gravity. The question I have for you is, what would happen if the earth were to double in mass? What would happen to the force of gravity acting on you? So let's go through and calculate it out. The first place to start would be to start with Newton's law of gravitation. So force of gravity equals the gravitational constant, capital G there, multiplied by the mass of the earth, your mass, which would be mass 2, and the distance between you and the center of the earth. We don't need to know these numbers to do this. We just know that they're all going to stay the same, because we said what would happen if the Earth's mass would double. So the only thing we have to do then is, instead of putting in mass, we'd put in 2 times mass. And so we did that there, and then all I did is I just pulled the 2 out in front, and this is allowed to do with multiplication. It doesn't matter the order that you do, so we can just pull the 2 out in front. It makes it a little bit easier to see, because now if you take a look, you can see that we have a G, m1, m2, d squared, which is what we just had before, where we said that was our original force of gravity. So the only thing that changed by doubling the mass of the earth is we ended up doubling the force of gravity acting on something because of that 2, and so we would say that you end up having 2 times the force of gravity. Now this shouldn't be too surprising to us, because we know that mass and the force of gravity are directly related, so whatever you do to one, you have to do to the other. So let's take a look here at another problem. What would happen if the earth were to double in size as opposed to doubling in mass? What would happen to the force of gravity you'd feel? So let's go ahead and put that in. This time though, what's going to happen is we are going to put the 2 times down in for the doubling of the distance. So when we do that, you can put the 2d down in below, and if we move a little bit to the right there, what you end up doing is when you pull that 2 out, remember that it is a d squared, so whatever you do to the d, you also have to do to the 2, and so you end up getting 1 over 2 squared, or 1 over 4. And what this would mean for us, if we take a look, we can still see that same force of gravity that we had before. And so if you multiply it by 1/4, you're going to have 1/4 the force of gravity acting on you. Okay, so let's go ahead and take a look at the next one. What would happen if both the mass of the planet and its radius were to increase? So it gets both bigger in size, that's the radius part, and in mass. Let's go through and do it just like you normally would. So we've punched the numbers in. We can see that if you put in 2 times the mass and 2 times the distance, when you factor those out in front, you'd have 2 times over 2 squared. And then if we take a look here, that would simplify down to 1/2, and we have that original g m1 m2 over d squared. And so what this would mean is that you would end up having a force of gravity that is 1/2 what you currently do. Okay, here's your 2 problems I'd like you to try on your own. What would happen if you went to a planet that had 4 times the mass of the Earth, but it was 1/2 the radius? How would you weigh on that planet compared to what we have here on the Earth? So it's smaller, but it's more massive, meaning it's just made out of really dense material. And then the next question I'd like you to take a look at is what would happen if you went to a planet that was smaller? So it had half the mass, but the distance between you and the center of that planet ended up being 1/3 the amount. Go ahead, try these on your own, and then I will reveal the answers to you in just a moment. Okay, so the answer for the first one here would be you'd put in 4 times the mass and 1/2 the distance. The 4 times the mass would increase the force of gravity. 1/2 the distance would also increase the force of gravity. When you put that together, you get 4 over 1/4. 4 over 1/4 simplifies down to 16 times the amount of force of gravity that you used to have. So you'd weigh 16 times as much. We take a look at the next one. If you had 1/2 the mass, this would act to decrease the force of gravity, but the reducing the distance, making you closer there at 1/3, is actually going to increase the force of gravity. When that simplifies through, you get 1/3 squared, which is 1/9, and when you do 1/2 divided by 1/9, you end up getting a decimal of 4.5 times the amount. So there you are. There's a few more examples on how to do that. Hopefully this helped you out. If not, we'll see you in class.